people coming. Okay, but let's start. So good morning, everyone. My name is Francesco Petruccione, and I'm the interim director of NITheP. Yeah, as you know, the summer school is a joint effort between the CHPC and NITheP. And during the first 2 weeks, you had a very nice introduction to Unix, to Linux, and Python. Yeah, and today we want to start the part of the summer school where you see how you can use Python and other tools to efficiently address interesting topics. Yeah? And the first lecture this morning will be by Dr. Mary-Jane Bopape, that you see already up here under the panelists, and I will pin her down now in Zoom so that you all can see her. Yeah. So thank you very much, Mary-Jane, for being with us this morning and for offering to coordinate a kind of a mini school on Earth system modeling and climate change modeling. We really appreciate your effort and your help to be with us this month. So without further ado, Mary-Jane, if you would like to start by sharing your screen, you're most than welcome, because people are here to listen to you, not to listen to me. Yeah, so you're more than welcome to start. And maybe just a reminder to the participants that we set this up as meeting because we want it to be interactive. Yeah, so I'm sure Mary-Jane doesn't mind if you ask your questions during the presentation, but of course there will be enough time for questions at the end of the talk. And please ask questions, because we would like last year to have a book prize for the best questions. Yeah, so we will every day choose a best question and reward after the summer school with some book prizes. So please, Mary-Jane, you're welcome to start your presentation. Thank you very much.
Okay, thank you very much, Francesco, and thank you for giving me this opportunity to come and share with you what the work we are doing as meteorologists. And my hope is that as a discipline, we'll also get to benefit a little bit from some of the delegates here that are attending here to learn. Hopefully some will be interested in meteorology or in weather and climate modeling as a whole. So the sessions that I'll be responsible for, they have been titled Systems Modeling and Climate Change Modeling, but in the presentations will mostly be focusing on atmospheric modeling. We are going to have 5 lectures. I'm here really today to set the scene, so I'll give just an overview of how models work. And I work at the South African Weather Service. I'm Senior Manager of Research there. I've invited 2 other people that are also working in the research department at the South African Weather Service, Mr. Robert Maisha, who will then take you through the steps that we follow when we run an atmospheric model. So you can already think with any modeling, you'll need to do some pre-processing. Then there will be the component where the model is really, running, solving equations and making predictions or producing a hindcast if it's historical climate that you want to simulate. Then there will be the post-processing part where you now analyze the output from the models. Then we will also have Mr. Lisitsha Lekolwane. He's also at the South African Weather Service. He's a data scientist there. He's also an MSc student at the University of Witwatersrand, where his master's is focusing on planetary boundary layer schemes. And he will share the work that he is doing in his master's so that you see how one can use an atmospheric model to answer some research questions. Then you will get 2 sessions from Dr. Nganyiso Mbatha. Dr. Nganyiso Mbatha is a lecturer at the University of Zululand, and I think of all meteorologists I know, he's the one that knows Python best. And in his description of work that he's going to introduce, he said, you are going to have fun with Python. So he'll show you how to use Python for geosciences. And the type of data we deal with in atmospheric modeling is multidimensional, and we also use different formats. So in his session, he'll show you how to use different types of data, analyzing, station data, analyzing three-dimensional data. So the first question I guess one will have is, why is it important for us to do this modeling? Why is it important to do weather modeling, to do climate? I went on to Google and I just searched floods in South Africa, and floodlist.com came up, and just from that website you can already see that within 2022, we are still really at the beginning of 2022, but you can see that we've already had a lot of flooding events. That is because we are in what is called a La Nina, is what we call the El Nino Southern Oscillation, and it refers to the state of sea surface temperatures in the equatorial Pacific Ocean. And when these sea surface temperatures are below average, we have what we call a La Nina. And due to what we call teleconnections, South Africa gets to experience above normal rainfall. And this above normal rainfall this summer season has been associated with a number of flooding events. So you've seen, these are covered on the news, so you've seen a lot of headlines. Now, the reason why we would then want to do modeling is because from models we can get forecasts. So we've got different timelines that I'll speak to, but with the forecasts, what you basically get are early warnings, and with the early warnings, you can reduce the severity that is associated with disasters, or when there is a severe weather event that is approaching and you want the public in time. Lives can be saved with property such as houses. There isn't a lot that you can do to try save those, but with lives, with movable property, you get an opportunity to save some of these. Now, so the issue of weather and climate is acknowledged in a lot of basically legislature. You look at a global level. You've got the United Nations. You've all heard about the Sustainable Development Goals that replaced the Millennium Development Goals in 2015. And with these Sustainable Development Goals, there's basically plans to say by the year 2030, this is what we would like to see. Zero hunger. They speak to health. We speak to the issues of poverty, issues of gender equality, and there is a goal 13. Which speaks to climate action. And there's an acknowledgement that this particular goal, if we work hard to achieve, the indicators that are associated with this goal, these will also have an impact on other sustainable development goals. If you consider, for example, the one on zero hunger, if you plant and some hailstorm comes and destroys whatever it is that you have planted, then the food is not going to be available. We've been hearing on the news that the food prices may go up here in South Africa because we had too many heavy rainfall events. And we know that the food prices can also go high when we get drought. So this climate action speaks to climate resilience. So it speaks to the inclusion of climate change in policies. It speaks to education awareness. When a weather system comes, you need to know what's happening in climate change. We need to be aware of what it is about. It speaks about also raising money from the countries that we know as being responsible for most of the climate changes as we know it. Then we can look at the African continent. So there is the Agenda 2063 of the African Union. They've set priorities there. Again, they speak to kind of similar things that are indicated in the Sustainable Development Goals. And one of the priority areas of the AU with the Agenda 2063 is climate resilience and natural disasters preparedness and prevention. And there are studies that have been conducted over the continent, and they indicate that the majority of the disasters that we experience on the continent are hydrometeorological in nature. So we know we can have, with COVID itself, we know there was a biological disaster. We know you can have earthquakes, it does the geosciences. And then when you get flooding, when you get, events such as, the Idai tropical cyclone that we know killed over 1,000 people. So those are hydrometeorological in nature. Then we can look nationally. So in South Africa, we've got the National Development Plan that speaks to its basically what we want to look like as South Africa by the year 2030. And there is Chapter 5 in the NDP that the Ministry of Environment is responsible for. And that Chapter 5 is called Environmental Sustainability and Resilience. And there's an objective within that chapter that speaks to improving disaster preparedness for climate extreme events. So that in itself tells you that when you model weather or when you model climate, this is something that is considered in any. So basically, you can look at different levels of government. South Africa also has the Disaster Management Act that talks to actions that the government needs to take across different spheres, at provincial as well as at local level, district as well as local municipality levels, the actions that need to be taken. And when it comes to hydrometeorological events, we need weather models to be able to forecast what is happening. In South Africa, we've got the South African Weather Service Act. I've already mentioned that I work for SOURCE. And we've got a mandate to provide meteorological services for public good and commercial services. So you can also, sell weather information. So there are private companies in South Africa. There are private companies across the globe that sell weather information. If you go to any country, so during the opening, I got an indication that it's not just South Africans that are attending, but if you look at just across the globe, there will be meteorological services, and we are all members of the World Meteorological Organization. And that means the World Meteorological Organization kind of provides standards for us to follow so that, when we issue a warning, it's not basically as far as the science is concerned, is to make sure that there are standards that are followed with the observation network, with the models that we are running. And in South Africa, the South African Weather Service is the only organization that may issue severe weather-related warnings. And this is to ensure that there is one authoritative voice when it comes to this. We have had incidences in the past where there were, there was information shared on WhatsApp to say there's a big storm that is coming when there was no such. There was a lot of chaos in Gauteng. There was a lot of traffic. People got to leave work really early when there was no such a system. I was still at the South African Weather Service then, in our phones were just ringing, uncontrollably. Now I'll get into the actual science or how we do the forecasting. And when we talk about really the basics that you need to be able to forecast, we talk about observations and we talk about models. So the first, there's a line in between. I put observations on the one side and then I put models on the other side. The one that shows a map of South Africa with some circles around it, that shows you our radar network, our weather radar network. We've got a weather radar network where the atmosphere is observed in 3 dimensions. What we are mostly interested in with our radar are thunderstorms, because they develop rapidly. And, you know, when you get this information in 3 dimensions, we can tell where, you know, you've got ice inside the cloud, and we can also we've developed some algorithms that can tell if there's hail that is associated with the storm. The one just on the right, shows you where we've located some activities. It's basically high reflectivity that is associated with a lot of ice. And there's a cyan color that shows the current position, and then you've got a red color that shows where the storm is going to move in the next few minutes. Then we also have a lot of basically ground observations. We've got automatic weather stations, we have automatic rainfall stations, we have manual rainfall stations that provide us with 24-hour rainfall. So those are actually in the majority. With the automatic weather stations, we've got a limited number. Then we also rely on satellite information. So the South African Weather Service uses Meteosat 2nd generation, and it is a geostationary satellite. So you've got satellites that are orbiting, and when they orbit, you find that they can observe one point on the Earth's surface twice in a day, while with the geostationary satellites, they are just in one position and they are able to observe the one part that you know, they are able to view a number of times. So the Meteosat 2nd generation that we are using mostly provides us updates every 15 minutes, and in that way we are able to check what is happening with thunderstorms. Now, if we had just observations and without the models, the way that I'm going to describe them, the longest lead time that you could probably get is about 2 hours. But for us to be able to forecast anything, let's 6 hours ahead in time, or to forecast for tomorrow, to forecast for 2 days, making a forecast today for Wednesday, or for 3 days from now, or even for 2 weeks, to produce seasonal forecasts, to produce climate change projections, we rely on models. Now, there is that figure there which shows, you could say, the globe, and the side that's facing us now is Africa. You see lines there, lines of longitude and lines of latitude. So lines of longitude, they going from north to south, and lines of latitude east to west. And the way to think about a model is that where the 2 lines meet is where we make our calculations. Then the distance between 2 parallel lines is, you can think of that as it's grid spacing. We call it resolution, but strictly speaking, it is not resolution. But generally, when people say this is the resolution that we are using, they mean the distance between 2 parallel lines. So when you are looking at, suppose we had to make simulations across the whole globe. So where the lines are meeting, that is where we will be making calculations. The types of equations that we are solving, you can see them there on the right. It's conservation of momentum that we are concerned about, conservation of energy and conservation of mass. And we also use the equation of state, which relates pressure to temperature. Now, the reason why we are, relevant when it comes to high performance computing, why we are part also of the summer school, is because for us to run these models, we need high performance computing systems. So I talked about the issue of resolution. I'll get into it some more now as the slides, as I continue with my slides. But the available computational resources determine the available computational computational resources determine the resolution that we are able to afford as meteorologists. So if you think about this slope, and I say that spacing between the two lines, the two parallel lines, is if it becomes really small, that means you are going to end up with way too many points that a computer will need to solve for us to be able to get a forecast. So generally there are some compromises that we have to make, and we use a resolution that we know is affordable computationally. The supercomputer that you see down there that's written Cray is a Cray XC30 that we have at the South African Weather Service that we use to produce operational forecasts. Now, I hope that as I was talking to the 2 points, observations and models, you could see that if we are talking about early warnings, that process is not completed. So you will get, output from the models. You also have your model, your observations. The models are not perfect, so there's some bias correction that we have to do. The models are also associated with some uncertainty. So usually we will make multiple realizations of the same forecast, and we call that ensembles that we can compare. Then there are some time scales, in particular what we call nowcasting, from about 2 hours up to about 6 hours, where you need to match the observations with the model output. And we hope that with machine learning can also assist us when it comes to post-processing. Then there's human intervention that is needed. So the warnings that you see on TV are produced by forecasters at the South African Weather Service. So we've got forecasters that sit, they are there 24/7. They produce the forecasts that go out, and twice a day there is an email that goes out to radio stations, that goes out, to TV stations, where we provide them with information on the maximum and minimum temperatures, the expected rainfall, and we also provide them with information with warnings of severe weather. And we also have a mobile app. At this stage, I think almost everybody has a phone. So with our mobile app, you can also see minimum and maximum temperatures and see forecasts going up to 7 days ahead. And we also have what we call climate sensitive sectors. Agriculture is one of those. We have health, we have energy, we have the water sector, as well as disaster risk management sectors, where we develop products for them. And the word that is used a lot these days is co-production. That is, meteorologists, we shouldn't just be developing products and just dumping them and expecting users to accept them and use them the way they should. So these days we talk a lot about co-production. That is, a meteorologist, I need to sit with a farmer and get an understanding of what their needs really are, and using output from the models as well as our observations, doing the bias correction, then we can develop products that the farmers will find useful. Now, I talked about time scales. So going from the left there, we have the shortest time scales, and then we can go all the way to the right, which is, the long time scales. You've heard these weather. Weather is really the short-term stuff. So what is happening right now, what is happening outside, that is weather. Now, when you start talking about the long-term things, when you talk about the season, for example, or even when we talk climate change, we're not talking about something that is happening, in a short space of time. So we've got weather, we've got climate, but the models that we use actually to do weather, to model weather, the models that we use to model climate are similar. But as you go to the longer time scales, it becomes important to now start using Earth system models. Right now, I said the focus of this particular talk is going to be atmospheric modeling, but you also have different components of the Earth system that you need to model, especially if you want to be able to do climate change projections. So you want to know what is happening with ice, you want to know what is happening with the oceans, you also want to know what's happening with the biosphere. So the Earth system models try to incorporate all these processes. But generally you find that as a scientist, one will focus on the one area. So myself, the reason why I'm now the top focus is on atmospheric modeling is that I'm an atmospheric modeling specialist. Then you have people that will study and focus, on oceanography, and maybe they will develop ocean models. And then you've got people, usually it's meteorologists as well, that will look at land surface models. Then there are two black lines that are shown there, indicating that as you increase the time scale, the uncertainty is increasing. Francesco, can you just tell me, is my background, is it okay?
Yes, Mary-Jane, it's just perfect. We can see the screen very nicely. It's absolutely fine. Thank you.
Okay, so the background wise is fine. It's not okay. Thank you.
It's okay. It's okay. Thank
you. All right. Thanks. Okay. So I've already said this now a number of times, that with the atmospheric models that we are using, we use them. They are really similar across a different time scale. So the top one is the one that looks at conservation of momentum. The time on the left basically says it's basically the full change in wind. So it's wind in all sorts of direction. In U, we've got what we call U. Usually it's change in the east-west direction. We have V which is the change in the wind in the north-south direction. We have W, which is wind in the vertical. And the processes that are important to consider we've got the pressure gradient, we've got the Coriolis force, so that is the fact that the Earth is rotating, and as it rotates, then you've got a deflection of the winds because of that. Then we also have buoyancy. So the way to describe that is generally that when we get, when we usually think of it as an air parcel, to say when the air parcel is there and it's hotter compared to, or it's warmer compared to its environment, then it will rise. So that is what we'll consider in terms of buoyancy. Then we also have mass conservation. So with mass conservation, we do consider the wind as it is, but then with the water vapor as well as liquid as a whole, we also have what we call water continuity equations. Then we also have conservation of energy. The way that it is displayed there is in the most simplistic form, because that is for an adiabatic system where there is no heat that is coming in. But we know that in the real atmosphere, you've got the sun that is heating up the surface, and we also have some long wave radiation, which is now heat that leaves the atmosphere into space. The observations that I talked about automatic weather stations and a whole lot of satellite information can be used as initial conditions. We initialize the models with observations that we obtain, and we also have what we call boundary conditions. I'll speak a little bit more on the boundary conditions in as far as they're related to limited area modeling, and we use numerical techniques, to solve these equations, these partial differential equations. And as I mentioned, you can just think of, how we solve these as, basically, you can think of that we solve these equations where a line of longitude meets a line of latitude, and that this distance between the two parallel lines determines your resolution. Now, when we develop models, there are some tests that we can conduct. Some of you may have listened to Professor Francois Engelbrecht. What you see down here, what you see in these figures is what he produced in his PhD. So on the left, you see the equation sets that he used. So he introduced a warm bubble. I'm not showing what the colors indicate there, But where you see a reddish color, that means that is where you've got, the highest temperature. And then you can see as you move outside of the bubble, the temperature is is decreasing a little bit. So when you introduce a warm bubble in the atmosphere, the expectation is that it will rise. So when you develop a model, you will set up such experiments where now you can see that bubble was there, it was introduced with, I'm showing that it says T equals to 0. So that is just when you are starting with the simulation. And then after 350 seconds, you can see that it has risen a little bit. And then after 550 seconds, you can see there it continues to rise, and then it's kind of dividing into two. And then by T, so this simulation was made up to about 900 seconds, and then it just gets there, and then it stops there. So this in itself is a good test, and then it shows that the model does what it's expected to do. You can also add a cold bubble. When you add a cold bubble, then the expectation is that it will sink. So I also worked with this equation in this equation set in my PhD, because my responsibility was to add cloud microphysics to the model, and then after that, we're able to simulate thunderstorms with it. Now, so with models, there is a long history to them. The first successful numerical weather prediction forecast was made in the 1950s. The resolution that was used then was really cost, because the computational resources then were very limited compared to what we have at the moment. Now we've got processes that the models are able to simulate explicitly. You also have processes that are subgrids. So by subgrids, so these are processes that are smaller than what the grid is able to capture. And these processes, they are parameterized. And as far as we know, the parameterization schemes are the ones that are responsible for most of the uncertainty in our simulations. And as I mentioned, with high performance computing, we do need high performance computing for us to be able to run models with high resolution. So ideally, we would run with higher and higher resolution so that we rely less and less on parameterization schemes. But I'll show you in some of the slides how the parameterizations work. Now, we've got what we call limited area modeling. The figure that you see in that plot shows you exactly how that works. You have a model that runs over the whole globe. To be able to run that model with high resolution, you are going to end up with too many points. That means the computations will be too expensive. But we want to get high resolution simulations. If you are running a model, suppose the grid length is 500 kilometers, so you can imagine that there is a lot that you're going to miss in terms of topography. But if you are able to reduce that such that, let's say the grid length is 3 kilometers, then you will be able to capture the topography in a better way, and that will also have an impact on the skill that is associated with the model that you are running. So what we have come up with as meteorologists is what we call limited area modeling, where you run a global model with a slightly low resolution, and then select an area that you are interested in where you run the model with higher resolution. As you are doing that, the global model will feed the model with time-dependent lateral boundary conditions. Initially, the updates were made every 6 hours. Now we are seeing, the meteorological services moving into a direction where these updates, the lateral boundaries from the global models, are made every 1 hour. The ones that we've got at the South African Weather Service, it's every 3 hours. We also have a variable resolution is also, in a way, we call it limited area modeling, but with this one, the model runs over the whole globe. I imagine I've not had a chance to catch up with the presentation that Francois Engelbrecht made on Friday, but most of his work is based on this a model. The model that he's using is called the conformal atmospheric model, where you run with high resolution over an area that you're interested in. And as you move away from the area that you're interested in, the resolution gets lower and lower. So there are two images that I'm showing you. There is one where we can say we've got quasi-uniform resolution. So the resolution is almost the same across the whole globe. And then you can have one where you've got higher resolution over the area you're interested in. The example shown there, you can see it basically, it's black over Cape Town because you've got a whole lot of grid points there where there is really high resolution. I think for this one, it was 1 kilometer over Cape Town. And then as you move away, the resolution gets coarser and coarser, obviously, to the point where there isn't much in terms of the number of grid points on the other side of the globe. I should mention that this is a model that we are concentrating on our model development efforts. So this is work that's being done by the South African Weather Service. We are collaborating with University of Witwatersrand, the Global Change Institute through transfer, and we are also working with the University of Pretoria as well as University of Zululand on this project. So the models that we are using currently in South Africa for operational purposes, as well as to inform policy developments, were not developed here in South Africa. So we want to develop the capacity to have models that we can improve ourselves to improve weather forecasts over South Africa. And for that, we need local knowledge to make it into models. So we've decided to focus on this particular model because we know that developing a model from scratch will take really long. I mentioned that Francois developed the model where I showed you a bubble that's rising, and that in my PhD, I added cloud microphysics schemes. So from that experience, we know that it will take really long to develop a model from scratch, especially when you don't have the capacity. So CCAM is a model that we are using now to develop model capacity in South Africa. Brazil and Norway followed that same route where they started developing models from elsewhere, and as time went by, they improved the model so much that they started taking the identity such that we can say now the model is a Brazilian model, or the model is a Norwegian model. So I mentioned the issue of resolution. The resolution that we use in models determines the name with which we call the models. Global models generally run with lower resolution, and that is because to run them with high resolution, as I mentioned now a number of times, you are going to end up with too many points. You will end up with too many calculations that you have to make. In terms of the resolutions that they're operating with, you've got those, for example, when you look at climate change projections, the grid length is around 100 kilometers. And the models that are being used for numerical weather prediction purposes, there are models that are now running with 9 kilometers. I'll mention which one in soon. Then we have regional models. As I mentioned, these ones, you only run them over an area that you are interested in. And in that way, you are able to get higher resolution than what is possible with a global model. Then we also have what we call, cloud resolving models. So cloud resolving models, so we mean these are models that can be able to resolve clouds explicitly, where you don't have to use convection schemes to parameterize clouds. Then we can also go into the other side where we've got large eddy simulations. I hope I'll be able to discuss a little bit more on how the large eddy simulations work. Now, depending on which model you are using, some of these will become parameterization schemes that you are using. For example, there's deep convection there, which you don't parameterize if you are using a large eddy model or if you are using a cloud resolving model, because deep convection will be resolved explicitly. Then you've got turbulent mixing, for example, that you have to parameterize in all these models, because when we talk about turbulence, you start off with some really small eddies, and then you also end up with some large eddies that can be resolved depending on the resolution that you are using. So with this figure here, I just wanted to show you the effect that is associated with resolution. What I'm showing you there is topography, the colors that you are seeing there. So you basically have blue, which goes from basically about sea level, and then as you go higher and higher in altitude, then it keeps increasing. And you can see that one, it shows exactly what topography looks like in South Africa. And on the left, the grid length that was used there is 9 kilometers. And on the right, the grid length that was used is 3 kilometers. And by just comparing the two, you can see that the 3 kilometer one has got a lot more detail. I hope you can see that difference, that there is more detail in the 3 kilometer one. And in this way, so if you are able to capture your topography better, then it will also have an impact on the quality of the weather simulations that you can produce. Now, just to give you an indication of the types of resolutions that we are using. So initially I said that with weather forecasting, we started around the 1950s, and the grid length that was used around then was, you could say, around 500 kilometers. So you'll have one calculation here, and the next calculation you make will be about 500 kilometers away. Right now, at the big centers, make simulations with a grid length of around 10 kilometers. The UK Met Office runs their unified model, the global atmosphere, with a grid length of 10 kilometers. So every 10 kilometers, there's a calculation that is made. Then we've got the ECMWF. As far as we know, this is the best model that we've got. They run a model called the IFS, Integrated Forecast System. It runs with a grid length of 9 kilometers globally. Then there is a DWD. It is in Germany. ECMWF is basically a European center, so it's a center that is funded by different member states of Europe. The UK Met Office is specifically a model for the UK. Then there is a model called ICON, which is developed by, its development is led in Germany by DWD, which is a Met Service of Germany. And they are running that model with 13 kilometers for numerical weather prediction. So running models at this scale, we are not doing it in Africa. We just don't have the computational resources to be able to afford this. So what we use is limited area modeling, where I said you run with high resolution over the area that you are interested in. Now, this is just to give you an indication of what we have here in South Africa. The South African Weather Service, as I mentioned, we hold that mandate to provide meteorological services, and we are the only organization that can issue warnings of severe weather. We've got that CRAE XC30 there that you see at the bottom right corner. When you go to the big centers, UK Met Office and ECMWF, you'll find they've got duplicate systems that are much, much bigger than this HPC system that we have at the South African Weather Service. And they've got duplicate systems because the one system serves for failover. So if the main one that they are using for their operations fails, the forecasts are then made on the duplicate system. So here, for us at source, we've got just the one CRAE system. So when we experience technical difficulty, our model then on the CHPC cluster. The main operational model that we are using is the UK Met Office unified model. So they provide us with information for the lateral boundaries from their global model that runs with 10 kilometers, as I mentioned. And what we do here in South Africa is we run over, you can see that we cover most of SADC with a grid length of 4.4 kilometers. And over South Africa, we run with a grid length of 1.5 kilometers. Just to give you an indication of how expensive these simulations are, when we make simulations up to 72 hours ahead using 72 nodes. 72 nodes on our system. You basically it's 1,728 cores. So our processors that we are using, we use Intel processors at the moment because our system is all these Ivy Bridge processors. So each node has 24 cores. And so our forecast takes 1 hour, 50 minutes to produce 70-hour forecast. And you can see why we need an HPC system, because now this information, after that, 1 hour, 50 minutes, the forecast need to go to the forecasting office, and the forecasters will have a look at what is happening, and they can issue warnings. We are using the same system, same HPC system to make seasonal forecasts. We run an atmospheric model that is coupled with an ocean model, and we update these forecasts once a month. We also produce climate change projections. At the moment, we are just starting with what we call dynamical downscaling or the regional modeling, which I've already explained. And for this, we are working with the University of Witwatersrand, and we are going to be using the conformal cubic atmospheric model, the model that was presented to you if you attended the seminar on Friday. Now, here I just want to show you examples of the type of output we get from the models. I chose here this event which happened in April 2019, where people lost their lives. It's actually over 70 people, 1,400 people were displaced. And it's reported that the amount of damage caused, it's over 1.5 billion. And the system occurred because of a weather system, which we call a cutoff low. This system is basically, it's a system that you can see when you look at the circulation in the upper atmosphere. It's called a cutoff low, and it usually results in an uplift over the eastern parts of its trough core. So, and then there was a cold front as well as a ridging high that were associated with the system. So as I mentioned, there were floods and there was loss of life. Now, in terms of what the models produced, I'm just showing you here over KwaZulu-Natal, because that is where flooding was experienced. That A plot there is our ground observation. Then I'm showing you different simulations from the models, and you can see that in general, so where you see the colors are reddish, yellowish, that is where we got the most rainfall. But you can see that the models kind of, got the event they got it okay. But what you also see is that they overestimated the amount of rainfall in the northern coastal regions of KwaZulu-Natal. So that is something we are realizing with these models when we run regional models, that they seem to overestimate the amount of rainfall extending towards the north of KwaZulu-Natal. So what I'm also showing you at different lead times, when we make these forecasts, we update them a number of times in a day. So you can see we say a 12-hour lead. So basically 12 hours before the 24 hours that we experience this rainfall. And we also buy data from ECMWF. I mentioned that this, as far as we know, is the best model. And you can see that the ECMWF actually got the rainfall in the southern parts of KwaZulu-Natal a little bit better, and it didn't really overestimate rainfall in the towards the northern coast. So you can see, so just to be clear, so this is the part where I say the rainfall has been exaggerated, and you can see it here with the 1.5 unified model 1.5, and with ECMWF you can see that the rainfall was not overestimated. So the models generally capture these high impact weather events, but then when you look at the details, there are certain processes that are not captured okay. This is just to show you, when you watch SABC News, you'll see maps that look like this. They will add different colors. When there's a higher probability, they'll show a darker blue color, and So for that particular event, these are the warnings that we issued from the South African Weather Service. I'm showing you where it says rain, it's output from the unified model. GPM is a rainfall product from NASA. TAMSAD is a rainfall product from University of Reading. And with that, I'm showing the associated forecast. This is the chart that went out to SABC for them to draw and add colors as they like them for that particular day. And then there were also alerts, and you can see where flooding was experienced. There is that tree there, which shows that we did say they were going to experience heavy rainfall leading to localized flooding. And then you can also see some parts there where we predicted severe thunderstorms. So we also produce seasonal forecasts. The grid length that we use is slightly, it's coarse. So you can think of it as being about 250 kilometers by 250 kilometers, which means when it comes to topography, we are not really able to capture much. But this is just to give you an indication with seasonal forecasting. I already mentioned ENSO that right now we are in a La Nina season. That is why we've been experiencing a lot of rainfall. We are getting out of that. So the forecast, the first row there shows you what is normally the climate average for February, March, April, May, June. And then below that, we are showing you the forecast. So basically the deviation from that average. And you can see that for February, March, April, now we are showing that. So this is now the forecast that we have issued actually from the South African Weather Service that shows we are expecting below average rainfall conditions. So you can see the brownish color shows that, and then if it's greenish, it shows that we're expecting above normal rainfall conditions. We also produce climate change projections. I'm not going to say much on these ones. My hope is that Francois spoke quite a lot. I'm checking my time. I see it's 8 minutes before 10, and I want to give you a chance to ask questions. So with this part, it's really just to give you an idea of what we have in terms of what I call parameterization schemes. We've got what we call cumulus schemes that are there to basically model at a subgrid level, model what happens with deep convection. We've got different types. We've got what we call adjustment schemes that just try to adjust the temperature and moisture profiles to a quasi-equilibrium state. We've got mass flux schemes that try to compute, the actual processes, the updrafts and the downdrafts that are associated with these thunderstorms. And some of the schemes are scale aware, while others are not. We have done some studies where we compared different schemes. We've got a paper that is published that shows this, for example. So this was for tropical cyclone Idai, where we were comparing schemes. So the ones that you see in the middle were the GREL-F and MSKF are scale-aware schemes. The simulations here were made with a grid length of 6 kilometers. And when you look right there at the center, you can see the brownish color that is there. It's just the one that goes from 5 to 50. But when you look at this one, Betsmiller, Yannick, the NUSAS, and Titke, you see this color also getting into 50 to 100. And this to us shows us that the scale-aware schemes, when you are using higher and higher resolution, they will do less work. This shows you another example. So this is from the conformal cubic atmospheric model, which I said we are focusing on. I'll just show you. So just look at the second and last row. With C there, you've got a rainfall that with a simulation where the grid length was 3 kilometers. And on the last row, E shows you rainfall where the grid length used was 3 kilometers. Then below, so for D, that is a rainfall that resulted from the convection scheme with a grid length of 3 kilometers, and then F shows you rainfall from the convection scheme when we used a grid length of 9 kilometers, and you can see that the one with 9 kilometers produces more rainfall from the subgrid model. So this is what we want to see, because with 3 kilometers, we are saying the model is able to resolve the processes properly. At 9 kilometers, you still expect some subgrid processes to be missed. expect these processes not to be resolved explicitly, and therefore the subgrid model needs to know to do more. We also have what we call cloud microphysics schemes. So with cloud microphysics schemes, the model, there's condensation there, and you basically model water vapor as well as different hydrometeors. And by the hydrometeors, I mean cloud water, you have cloud ice, you have rain, you have snow, you have groupel, some also include hail. So you've got processes that we model that basically provide you its information back and forth between these different hydrometeors up until you get precipitation. So we have done some studies comparing different microphysics schemes, and basically the headline of the study was just that we didn't get much differences in terms of the simulations. It's different lines that we've simulated with different microphysics schemes. The WRF single moment scheme that had groupel and one that excluded groupel. We also used one called SBU Wyland that combined snow and groupel, basically all falling ice. And those lines here, the lines that I'm showing you with different colors, are from different convection schemes, and you can see they are very close to one another. When you look at the one below, so that is rainfall occurrence, and you can see that they all show rainfall occurring at around the same time. So information like this for a forecaster will result in a forecast that is somewhat similar. So something just to keep in mind, especially for us here on the continent, this is basically something that is applicable for Africa. We are a continent that has got sparse observations. So if you go to Europe, if you go to America, you'll find that they've got a lot more radar observations. They've got a lot more automatic weather stations, automatic rainfall stations. So for us, because we've got limited ground observations, we tend to rely on satellite information. What I'm showing you there is an example for ex-tropical cyclone Dineo, which happened in 2017. So that on that 18 February 2017, the ground observations showed rainfall as shown there in A. The NASA rainfall product shows rainfall as the way it is there in B. The ERA 5 reanalysis, so this is from ECMWF, the European center that I've mentioned, saying that it's got the best model now in the West, says that is the rainfall that was observed. And University of Reading has a rainfall product based on satellite as well. What is shown there on D, it shows what. So basically all of these are considered as observations. So you can see why obviously A is the truth, because it's really based on ground observations. So you can see the challenge we have as a continent if we continue the way we've been doing, in that we don't increase the amount of ground observations that we have. So we are going to struggle also with our modeling studies, because you don't really know what to target, because observations are different. So because if you think about satellite products, we think of them as observations. There are also what we call planetary boundary layer schemes. The boundary layer is the bottom part of the atmosphere where we are staying. So generally what they try to do is to model shallow convection. Not all of them do that. And then there are others that just consider mixing. I'm going to skip a little bit. So this is really just to say we've also compared different planetary boundary layer schemes, and we found that in terms of simulations, they are kind of mostly similar. But again, so this was a study we conducted for Zambia, where you find that there are challenges again when it comes to observations. So here I'm comparing the NASA and the University of Reading products, and all of these are, so each row, each column is the same day. And you can see if you look at 17 December, according to the NASA product, the rainfall that was observed in some areas exceeds about 75 millimeters. And when you look at the University of Reading product, there's basically the rainfall that was received, there's nothing more than 40 millimeters. So here, I'm gonna use this slide and then just jump to the concluding slide. But this one, I just wanted to introduce to you a problem which we call, it's the gray zone problem. That is what we are dealing with as meteorologists at the moment. I said that initially when we started modeling, the models were using really low resolution. And so there was a very clear separation between what we are able to resolve and what we cannot resolve. So the parameterization schemes deal with what the model is not able to resolve. And that is dealt with easily when the grid length is really it's large. So with the gray zone problem, we are saying now the grid length that we are using in the process that you want to model are about the same size. So you are basically at a point where you can't say you can resolve. The example I'm using here is with the planetary boundary layer. We've got, if you have a convective boundary layer, you have large eddies, and these large eddies, we say they scale with the planetary with the boundary layer height. So the boundary layer height is normally at 1 kilometers above the surface. So if I'm running a model, the grid length is 1 kilometers, and with that model, I should also be able to model the large eddy. Now, the problem is that the large eddy is also about 1 kilometer. My grid length is also about 1 kilometer. So this is what we call the gray zones, where, you can't say, if you use higher resolution, let's say I use a grid length of 50 kilometers, I will be able to resolve that large eddy. And if I use a grid length, say, of 50 kilometers, that large eddy is a subgrid process that I can parameterize. But now, if the model is running with a grid length of 1 kilometer and the scale, the large eddy's length scale is also 1 kilometer, then we've got the gray zone. So we are still trying to find out how to deal with that problem. I'm going to jump these ones and then just come to this one to indicate what I was saying in terms of, what is resolved. So the first row shows you total kinetic energy, where we used a large eddy simulation. We used a grid length of 25 meters, 50 meters. The different colors show the grid length that we used. Now, when you look at the one below, it shows you the energy that is resolved, and you can see that with the highest resolution, you resolve more. And when you use a low resolution, the lowest now, the grid length was 400 kilometers, so you can see that we resolved less. And then you expect the subgrid model to do more, so you can see the contribution from the subgrid model is with 400 meters. So that is what we mean with parameterization schemes being scale aware. Now, just one more point to make is that here, this is just showing you a cross section of the W prime, so deviation of the wind from the mean. So when you use a grid length of 50 meters, you can see the amount of detail you get there. When you use 400 meters, you can see that the resolution, the detail starts to reduce a little bit. Now, if the model that I'm using, I say the grid length is 10 kilometers, that means everything that you see in that box is represented by 1 point. So the parameterization scheme is supposed to give us an indication of what these processes here that we are not able to capture are going to do. So I'm just gonna now provide my final remarks, and then we'll move into the questions. So it's basically to say we've got a model development program here in South Africa. We are working with a number of universities. I've said this already. So with the work that we are doing, we need students that have got a maths and physics background. And in terms of modeling processes, there's the atmosphere. I mentioned for climate change studies, you want to use an Earth system model. So you need to have a model that can model. So, the Earth system model needs to have a component that deals with the atmosphere, one that deals with the ocean, one that deals with land, one that deals with the biosphere. So we also need to be collaborating with software engineers so that they can assist us, to optimize our codes. So Francisco, I'm going to stop there. I've not checked the charts yet, but I'm assuming the questions will be there. So I'll stop sharing so that I can.
Mary-Jane, thank you so much for a fantastic introduction to the topic. There are a few questions in the chat. But I would suggest if the participants that ask the question in the chat, since we are in a meeting, they are welcome to unmute themselves and ask the question directly so that we have a little bit more of an interactive element. And we are perfectly on time, so that there should be no problem. So I'm not sure. I think the first question was by Justice. Justice, are you still around? Okay, Justice, sorry, maybe while he tries to get in, Justice asked, thank you for your presentation. It is not my, but I have a question. If doing model is based on the collected data, how do you manage wrong data and lack of data in certain regions?
Yes, so that is a problem which I did mention, I think, when I showed you different products from satellites. So input data, we definitely need observations. The use of satellite has kind of helped us a bit. There was a time when the performance, the skill of models in the Northern Hemisphere was a lot better compared to the Southern Hemisphere. And that was because we didn't have much in terms of observations in the Southern Hemisphere. But with the introduction of satellite information into models, that has improved such that the performance is kind of almost at the same level. But as you are moving to higher and higher resolution, then it becomes really important for us to add more ground observations, more high resolution observations, which is why it's important that we continue to invest. So I can't say it is not a problem, but with we are managing to do what we can with what we've got available.
Sorry, I'm muting myself because I have a neighbor doing some renovations. Sometimes you can hear the drilling in the background. Sorry, I can't do nothing about it. The next question is by Floyd, and Floyd is here, I see. So Floyd, would you like to unmute yourself and ask your question? Floyd, I can see you. So you just need to press the unmute button. If you want, I can do it for you. Okay, it looks like our participants are very shy. Anyway, Floyd asks, would you advise if this model can be accurate and how accurate they are, especially when it comes to the climate data? Because I'm trying to establish how heat waves and possibly cold waves may affect plants, and this in turn will affect the livelihoods of the consumers of these medicinal plants, for example. Thank you, Floyd, for the question. Yeah.
Yes, so I think I showed that a little bit with the example of the KZN flat. When we get a really, a synoptic system that is strongly forced, the models are generally able to capture that. So if you've got a synoptic system, the models are really good with capturing those. If you've got some individual thunderstorm developing somewhere, the models are not that good with capturing that type of system. But all in all, in the studies that we conduct, I mean, it's with climate change projections, for example, the normal procedure that is followed is that you will make simulations. You don't just start by projecting, you make simulations for historical climate, and you take those simulations and then you compare them with the observations so that you can determine the biases that are associated with the model that you are using. So there are biases in models, which is why we need to do some bias corrections. Then you can use the model that is bias corrected to then be able to go further with applications modeling. But all in all, the models are able to capture the diurnal cycle. They are able to capture the seasonal climate, the interannual variability. They're able to capture that. When you've got high impact weather events, as I mentioned, they are able to capture those, although there are differences when it comes to the actual location where rainfall is occurring. So there is a lot that you can get out of the model. models. There are some improvements that we are expecting as we're moving to higher and higher resolution. As we get to understand, processes even better, the expectation is that we will be able to understand, we'll be able to improve these models better. But with what we have, you can be able to get the results that you are looking for. But first, you need to make sure that you bias correct the models that you are using.
Thank you, Mary-Jane. There is another question by Eric. I don't know, Eric, I can see you if you want to ask your question in person.
Thank you very much, Francisco. I can ask my question. Actually, I have several questions, but I put in one question just to give others a chance. And thank you very much, Dr. Bopape, for such a wonderful presentation. It actually makes us think, some of us think we are in the wrong profession. You guys are having more fun. You're having more fun with weather there. My question is, I suspect weather is regional in nature or global in nature, but probably let's talk about a region. You might then need to cooperate with neighboring countries in exchanging data, cooperating in terms of models and stuff like that. Are you having any problems cooperating with neighboring countries to exchange information so that you have a better picture of what is happening in terms of weather in this country, of course, in the region?
Okay. Thanks, Eric, for that question. It is an important one indeed. Weather does not respect political boundaries. We saw with the recent tropical cyclones, that would impact different countries. Idai was a good example that impacted Mozambique, Malawi, Zimbabwe. So we do need to exchange information. So the meteorological services are members of the World Meteorological Organization, and there are some resolutions there. So there's resolution 40, for example, that says we need to share information that allows, for early warnings to be issued. So the South African Weather Service does send some information to the ECMWF, which is then actually to the UK Met Office, which is then used in models to initialize models. Then secondly, South African Weather Service is what we call a regional specialized meteorological center. So this is a designation that you get from the World Meteorological Organization if you are able to provide information for different countries. So we've got a website that is available to meteorological services for meteorological services of all 16 SADC countries, so they can log into that information and access our model output. And we also make model output from other different centers available on this website for other meteorological centers to use. But the WMO does make engagement between different countries possible. When it comes to sharing of ground observations, we ourselves here in South Africa don't share all of our data. We do share some of the data to be used in the models. A number of different countries, they do share, also they select which data they want to share, because the minute you share it for it to assist with modeling across the whole globe, some of this data becomes available for free on some website, while the Met services want to continue to sell this data. So it's data that is used, to assist with some revenue. I know, in the way that I'm responding, so there is some sharing that is taking place that is made possible by the WMO. Yes, so sharing of data is also, there are data policies, obviously, that will speak to data that needs to be sold and therefore doesn't need to go out to the public.
Thank you, Mary-Jane. The next question is by Monekiwa. Monekiwa, please unmute yourself and ask the question.
Thank you very much, Dr. So knowing that the atmosphere is it's a fluid in itself, and we're using models, mathematical models like the use of the Navier-Stokes equation, and such, the system can change very fast. So what kind of error could I say this? And how can we develop and change such models very fast and efficiently to use, because I think sometimes we get where the weather service that says that we might be looking at this type of a day where we have maybe a rainfall in the morning, but we end up not having rainfall, and the data changes fast. So how can we develop and improve such in this case? Thank you.
Okay, thanks, Makiwa. So yes, you are right that the atmosphere changes a lot, and in terms of the updates, we need to be trying to produce rapid updates. The way we started with modeling was that you would find that the updates are made just once a day. At the South African Weather Service, for example, you run a model, we update the models 4 times a day. Then you've got centers that are better resourced with computational resources that produce even more rapid updates. There's an example in Japan where they are using radar data to initialize their models, because I mentioned with radar data, you basically get the best information available when it comes to the state of the atmosphere. So as soon as they see that there's a thunderstorm that has come up, they update their models quickly and they produce forecasts quickly to indicate the type of impacts that will be associated with that particular thunderstorm. But you do need to be able to act really quickly to say, now you are going to be providing such rapid updates. In fact, radar itself is not quite used as readily at the moment in weather forecasting, because the thinking is that yes, you will observe a thunderstorm with radar, and then by the time you finish making the simulation to forecast the thunderstorm would have dissipated. So I guess the only way is just to say we need more computational resources, so that I guess when the thunderstorm starts, or we can get an indication that it's coming up, we can make the forecast really quickly with many cores, so that the forecast will finish really quickly and we can issue the warnings quickly.
Thank you, Mary-Jane. The next question is by Fortune. Fortune, please, you're welcome to ask your question.
Thank you for the opportunity to ask. What I want to know is regarding the resolution of the calculations. Let's say, is it possible to use machine learning to increase that resolution after the fact, like after the calculations? Let's say we want to increase it from 9 kilometers to 3 kilometers after a calculation. Is it possible to use machine learning to do that? And another question I have is, in what other ways is machine learning useful? Like, how can you use machine learning in other ways in climate science or climate?
Okay, thanks, Fortune. Yeah, yes, it is possible to increase the resolution after. So I mentioned in the presentation what we call dynamical downscaling. So in a way, that's kind of increasing the resolution, but the equation set is almost the same. You basically use the same type of model and run over a smaller domain to get high resolution. But we also have what we call statistical downscaling, where if you've got high resolution data that is of good quality, you can use that data to train the model. So you take output from this type of dynamical model that I talked about, then you train it. Either it could be observations, so you can train that so that it produces higher resolution. So we do that with what we call statistical downscaling. So your input data, kind of, if it was a linear system, then your X would be what you have from the model with lower resolution, and your Y will be the observations, and then you train that, and then you get your relationships. Like I said, then you get your M and C. Then after that, then you can take the model output for the future as your X again, and then you can get the output at higher resolution. So that is really how you can do it with statistical downscaling. Then with machine learning, where do we see it adding value? Is mostly with post-processing. So we can see, because we're getting more and more ensembles out of our models. So, with machine learning, the expectation is that we will be able to do, a quick analysis so that we can tell. I mean, we don't want the forecaster to be looking at too many output, too many models all at the same. So the hope is that machine learning can assist, the forecasters to be able to make decisions quicker. Then I also mentioned the parameterization, which is, it's basically statistical relationships that are used to relate the large scale systems that you can resolve and the small scale systems that the models cannot resolve. That is really what parameterization schemes do. So we also expect that machine learning will assist us with parameterization schemes.
Mary-Jane, thank you very much. There is also a question by Krishna regarding parameterization. Krishna, would you like to ask your question yourself? Because you just
Hi, Mary-Jane. Yeah, so on the same note, the parameterization, typically how long does one of these parameterization schemes take?
What do you mean take? How long?
In terms of time scale. So like your simulation itself takes about just under 2 hours. How long does this parameterization scheme take for you to run through it?
So the parameterization scheme will be, so it's kind of embedded, because you establish the relationship and then, you get some coefficients that you can say you are happy with. So as the model is running, the parameterization scheme will also be running with it. So the model, if we say the model takes 2 hours, that incorporates the parameterization scheme itself. I have not checked. I think now as I'm answering, maybe what you are saying is of the 2 hours, how much of that is taken up by the parameterization scheme. I've honestly not checked how much expense is associated with the parameterization scheme. But what I can tell you is that in the way that we choose which parameterization schemes to use, for operational purposes, we tend to go for those that we say are computationally less expensive. For example, with cloud microphysics schemes, we've got what I showed you is a bulk scheme. So we've got single moment schemes where there is an assumption that is made on the distribution of droplets in a cloud, but you also have model double moment schemes that can predict the distribution of the droplets, and they become more expensive. And you also have some schemes, they're called bin schemes, that are a lot more expensive to run, and we don't use them in operational models because we know that they are going to be expensive. But in terms of how much more expensive how much expensive are parameterization schemes versus, let's say, the amount of time taken by the dynamical part, I don't have that answer for you right now, but it's something that I can check, but it will take me a few months to make time to check that.
Thank you, Mary-Jane. We have 2 more questions before we can wrap up for today. One is by Frederick, and that sounds also like a technical question. Frederick, you're welcome to unmute yourself.
Thank you very much, Doctor. My name is Frederick Marshall from University of Limpopo. I just wanted to know if they include the radio sonde as well as the radio occultation data in the modeling. And if they are using the radio occultation data, which retrieval methods do they use and which one do they recommend? Thank you.
Well, Frederick, I think you are the one that got me asked the question I cannot answer. So I think the first thing is to say, yes, we do include, so in terms of the radio sonde information, yes, we include that. So whatever is available. We don't do data assimilation as such at the South African Weather Service. So we leave the responsibility to basically analyze the satellite information to the UK Met Office. So the UK Met Office takes as much information as is available from the satellite information, and they send us that information ready for us to run. We are hoping to build capacity in the area so that we can have we can say we've got capacity locally to do the analysis of satellite information and use that information as our models, but at the moment there isn't. With the data assimilation system, as I say, is based on information that is analyzed by the UK Met Office. So I don't know what is best, and I don't know what they are using. So we just take what they send to us and we run the model.
Thank you, Mary-Jane. We have one last question by Yahaya. I hope I pronounced the name more or less correctly. And thank you very much, Yahaya, for raising your hand. You're the first one, so really much appreciated. I hope you will be an example for many others to come. Please,
sure. Good morning and good afternoon. My name is Bashiru from Ghana Meteorological Agency and Leibniz Center for Tropical Marine Research. I want to ask Dr. Marie if she has considered the effects of boundary and initial data set in initializing their model. That is my first question. My second question is I want to know the name of the model being used by the South African Weather Services. That's my second question. In her last remark, I showed that she was saying student with physics, meteorology or something background. Is it that they are taking students for training in such an area of model development or what? I want to be clear on that. For a PhD or master or something like that.
Okay, thanks. Hi. So I'll start with, okay, so the first simple one is which model are we using? For numerical weather prediction purposes, the main model we are using is the unified model developed by the UK Met Office. We also use WRF, the Weather Research and Forecasting Model, it's a community model whose development is led in the US by ENCA. We use it basically for business continuity. So in terms of the effects of the initial conditions and boundary conditions, it's something I did a long time ago for seasonal forecasting purposes. So there we're just checking if it's necessary to perturb the initial conditions for seasonal forecasting, because that is what we do generally for numerical weather prediction to come up with the ensembles that we are using. I can't say, we look at the impact and then consider what to do with it. We've got an ensemble system. It uses more graphs from the UK Met Office, so it's really different initial conditions that we then use for initial conditions as well as lateral boundary conditions in the unified model that we are running. And that is just a convective system, and we give each ensemble member equal weight to produce, probabilistic statements that the forecasters will then use and to get some confidence on whether some high impact weather event is going to take place or not. In terms of the value of such a study, to look at how different do they become, we know it's, you've seen spaghetti diagrams that come up from these models. So it's not something we have done to basically consider how different are these different ensemble members. I don't see us doing that as such, because we already take into account the uncertainty that is associated with different conditions. Then with your question on students, we are struggling a little bit in terms of funding, but we do have some projects and are working with students. Last year, we actually ran a training program that focused on meteorology in February, where we kind of taught on Python, on atmospheric modeling. So my point of the remarks is basically to say we need more and more people for us to be able to develop models from scratch, to say we've got local models that were developed in Africa, and we need those people to have a background in maths and physics. We have a studentship program at the South African Weather Service, but it's a policy that just got approved. We are going to be looking at how we implement it, and the hope is that we will be able to get in some postgraduate students to come sit with us at the South African Weather Service while they're registered with some university, assisting us with the model development.
I have a last follow-up question. Am I allowed to ask?
Please go ahead, but quick, because we're almost running out of time.
Yes, and then the spin-up time for the models. Have you looked at the spin-up time for the models? That's my last question. Thank you very much.
Not really, but we think it's about, so we don't use anything from when we initialize up to 6 hours. So we just assume, so we've just looked at what other papers have published, and a paper that considered the UM in particular said it's about 6 hours.
Okay, Mary-Jane, if you have 1 more minute, I think there is Isaac with a cramp in his arm already. Can we allow him to ask a quick last question? Isaac, please, unmute yourself.
Yeah, good morning, everyone. My name is Isaac from Kenya, Ghana. Yeah, with reference to the parameterization, I always used to hear a friend presenting on that. I wish you could throw light on that for me. She used to talk about convertive parameterization, but looking at that time that she used to present on those things, my mind is also on my project, so I couldn't spend my time to also know much about what she used to present on. So I wish you could throw light on that for me. Thank you.
So Isaac, so cumulus parameterization. So the terminology I kept using was cumulus parameterization, but that also refers to convective parameterization. So the idea with parameterization is that you are only able to afford a certain resolution with your models. If you look at the CMAP6 models that were used now to publish the IPCC report, the AR6, which was published in August last year, the grid length that was used, a lot of them were more than one degree. So that means the spacing between the grid points is more than 100 kilometers. So that means if you've got some convective activity, some thunderstorms in between those points, the models are not able to capture those. So the convection schemes try to provide some information to say, now, if there were thunderstorms between those grid points, this will be the impact that is associated with those thunderstorms. This is the amount of rainfall they would come up with. And, you would look at the temperature as well as relative humidity and say, in terms of the grid box itself, the expectation is that this percentage of the grid box will be associated with that thunderstorm activity. So the convection schemes try to do that. There are some that I kind of say, the thunderstorms will just occur at random and try to include that randomness in their models. There are others that just say, no, we assume that the thunderstorms will be taking place within a quarter of the grid box. And then this is how they will impact temperature. This is how they will impact rainfall. And these convection schemes, as I said, we think of them as being responsible for most of the uncertainty or most of the errors that we see in the models, because there are a lot of assumptions that we make, because you need very high resolutions, resolution observations to know exactly what's happening with thunderstorms, to be able to relate them properly with processes that you can resolve. So at the moment, in some sense, when it comes to parameterization schemes, there are some areas where you could say we are sort of flying blind, and that is why the models are still not perfect.
Thank you very much, Mary-Jane. I would like, if I may, make a quick comment on the questions asked regarding students and the possibilities of doing masters, PhD, and so on and so forth. And that is that NITheP has a bursary program. Yeah, so participants are encouraged to apply for those. Yeah, and we also have internship programs. Yeah, where you can also spend some time at various institutions of your choice to learn a few basic skills. Yeah? So that was just a generic comment. And Mary-Jane, I encourage you to make use of that because NITheP is here to help. Yeah? And we also have research assistantships and things like that. So it's please, you can make use of it, and all the participants can take part in that as well. So I'm sorry that we went a little bit over time, but Mary-Jane, thank you so much for the very interesting start of your lecture series. And you probably saw from the many questions that we received that the participant found it very interesting as well. So the second lecture in this series will be on Wednesday morning. where I think we will go with Robert Maisha a little bit more in the details of running atmospheric models. So while today was a little bit more the good weather kind of talk, yeah, on Wednesday we will go into the details, and there will be things that maybe the participants can try on their own. Yeah. As a last advert, this afternoon at 2, we have the beginning of the next lecture series by Professor Zurab Janelice on Python-based introduction to mathematical proofs. Yeah? And that should be of interest to everybody. So please join us again this afternoon, and encourage those that haven't been with us this morning to join us this afternoon. So thank you very much, everyone. Mary-Jane, thank you so much for your time and the excellent lecture. And yeah, and we're looking forward to see how this mini course continues. Thank you very much to everyone. We'll see you later. Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you very much.